Hello, Year 7s. Welcome back to science. Welcome back to school. My name is Mr. Lead. For those who don't know, I'm one of the Year 7 science teachers. And today I'm going to be starting you guys off on your new topic. Okay, so we've covered states of matter, and we're pretty much done with that. We're now moving on to our new topic. I'm going to say what that topic is in a moment, but before I do that, I want to say a few things. First thing I want to say is that if you guys are stuck at home, the best way us teachers can help you is if you communicate to us. If we were back in a normal classroom setting, you'd be communicating to us by just putting up your hand and asking a question. You can't do that here in this setting. So what you need to do, if you ever have a question, you need to contact us, teachers, okay? We are going to be by our computers and ready to answer your questions when you need us, okay? So if it's a personal question, send us an email. Otherwise, type it in the forum, okay? But anyway, formalities aside, I'm going to be demonstrating a demo for you guys. For this demo, I've got this little thing. It's called a film capsule. You're probably not really familiar with it or never seen it before. These things are kind of obsolete nowadays, but what they used to be used for was to store film in. But what I'm going to be using it for is for a different purpose. Now, as well as this film capsule, I also have a little hydrolyte tablet. Okay, so these are the things where if you put it in water, it fizzes up like that. Now, is that a physical change or a chemical change? That's right, it's a chemical change because we're seeing a new substance being formed. We're seeing a new type of gas being formed. It's not just changing state. It's a chemical reaction is occurring for this gas to appear. So, what do you think would happen if I took my film capsule and I half filled it with water? It's a bit too much, actually. If I half filled it with water, and then I put my little tablet in here. All right. We're gonna do it, and we're gonna see what happens. All right. Let's find out. This could take a little while. Okay, that was a little anticlimactic. I've got to admit. I've seen this work better before. I'm going to play on your screen right now a video of this working a lot better. Okay, what you're supposed to see is that the capsule will fly up like a rocket. Okay. Instead, what happened was it still moved, it still popped out, but I think this capsule is really old and the lid's really weak that it's not going to do a good job anymore. You would see a much better demonstration of this, okay? But now, that being said, we can still talk about the science of what's happening. There's a few things that are happening. We can talk about the chemistry behind this. We can talk about how it's dissolving and how it's making gas, but we're not going to talk about the chemistry today. What we're going to be moving on to in our next topic is we're going to be moving on to physics. Specifically, we're going to be moving on to talk about forces. What I want you guys to be wondering and question yourselves, how come this capsule actually popped out like it did? What is actually causing it to pop? And the answer is there's different forces being applied to this capsule to make it pop. All right, so let's jump into today's PowerPoint. All right, here we are. So we're going to be covering forces, like I said. Now, with this topic of forces, we're going to be going over a few things, and you should be able to, by the end, understand a number of different things. You should be able to understand how we measure forces. You should be able to understand why certain things move the way they do. Why is it that why is it when a parachute is open, that causes a person to fall slower than when a parachute is closed? It's the same amount of mass, but why is it when it's open, it causes someone to fall slower? You should be able to answer other questions like, what does your weight have to do with gravity? You should be able to answer, why does some things accelerate while other things stay at a constant speed? That's all got to do with forces. Now,
this topic of forces is a really deceptively simple topic. And I say deceptively simple because it seems very easy and straightforward on the surface, but when you get into it, it's actually people get confused by forces all the time. So I really stress when you have a question and you're confused about something, contact us. Let us know and we can help you understand this topic. Okay? So forces, some straight facts about forces, some basic facts to begin with. Forces is measured in with a unit called newtons, so we can actually measure how much force is applied to different things. And that we can actually measure forces using a spring. All right. So we'll hopefully someday in school we'll get to a point where we're measuring forces with a spring balance. It'll make more sense. Things will make more sense later on why springs are actually used to measure forces. But at home, you've actually got things that can measure forces. Your scales, your kitchen scales, your bathroom scales, they actually measure force. They actually measure how much gravity is pulling down on an object. And again, we'll cover what that means later. But yeah, old-fashioned scales used to have springs in them. Nowadays, more fancy scales have these things called piezoelectric crystals, which basically work the same way as scales and springs. But anyway, that's a brief outline to how forces are measured. But the main thing you've got to understand is that there are three main ways we can apply a force to an object. Okay, so forces can be either a push, pull, or twist. Now I'm going to demonstrate that. Let me get my sock. All right, so like I said, there are three main ways that forces can be applied. These are not the three types of forces, mind you. There are lots and lots of different types of forces. These are not types of forces. These are three ways forces can be applied. All right? So the first way that a force can be applied is if I just push something. Okay? I'm pushing my sock. All right? The next way that a force can be applied is if it's a bit hard holding this, if I pull something. All right? And the third way is if I twist something. All right? Those are your three different ways, okay? So you push, pull, or twist, okay? Those are the three different ways forces can be applied. Now, what can forces do? Forces can speed up an object, or it can slow something down. It can change the direction an object is moving, or it can change the shape of an object. So with that all in mind, if I just leave this Rubik's Cube on this table here, just set it here, let me make that big screen for you. If I just set this Rubik's Cube on the table, are there any forces applied to it? The answer is yes, there still are forces being applied to this Rubik's Cube right now, okay? It's not moving, that's fine, but there still are forces applied to it. So you don't necessarily have to see something to move to have forces applied to it. In fact, anything and everything all over, anywhere you are, all on Earth, you're always going to have forces applied to you. Everywhere on Earth, things have forces applied to them all the time, okay? It's just that sometimes some forces are balanced and other forces are unbalanced. We'll talk about what those two words mean in a moment, but understand that you don't necessarily have to have something moving to have a force applied to it. Everything always has forces applied to it. Now, we can actually represent and draw forces. So let's say we got a plane here. This plane has 4 different forces being applied to it, or at least we're going to simplify it down to these 4 different forces. We represent our forces using arrows, okay? So we have the force of gravity pulling this plane down, the force of thrust, or just applied force, moving this plane forward. Lift is helping, this force of lift is helping lift the plane up, and the force of drag is stopping it from going, is trying to stop it from going forward, okay? At a point later on, you're going to be able to understand what the different types of forces are, but at this point, don't worry about memorizing these different names, just understand that there are different types of forces. Now, you might be able to see we draw forces and we represent forces with these arrows. Now, there's a particular way we represent these arrows. Okay, I'm going to show you guys how we actually draw these forces, and I'm going to show you them with the two demonstrations I just did. So the first one. Oh, by the way, there is something wrong with both of these demonstrations, and I'm going to walk you through what is wrong with each of them. So the first one, we've got two forces enacting upon our Rubik's Cube that was sitting on the table, okay? These two forces is the normal force, or just the inertia of the table, just preventing the cube from just passing through the table, merging through the table. And we've also got gravity, which is pulling the cube down. It's the reason why the cube isn't just floating in midair. Two forces are acting on it, and they're both acting equally on it. Because they're acting equally, we represent the arrows in equal size, okay? So the size of the arrows really matter. Now here's the thing that this drawing has done wrong. We need to make sure that the arrows are coming out from the object rather than pointing towards the object, okay? Some people always think, oh, I want to put gravity on top because that shows that gravity is pushing it down. No, we want to show the direction that gravity is pulling the object, okay? So arrows need to be pointing away from the object, and they need to be equal if they're balanced. But what if they're not balanced? What if one force is actually stronger than the other? Well, I'll bring you to the second demonstration here. So this is the film capsule demonstration. The applied force onto the film capsule from all the air that was stuck in there, all that air was pushing and trying to push the capsule up. That was a lot of applied force, and it was so much that we actually have more applied force than the force of gravity, okay? There was more force in the air pushing it up than there was for the gravity pulling it down, and that's why the capsule went up, okay? So when the forces are unbalanced, when we represent them with different size arrows, and the arrow that's bigger is the way that we see the object going, okay? So that brings us to balanced and unbalanced forces. So you got to understand that when forces are balanced, the object will not accelerate or decelerate, okay? So, for example, when you're sitting on a chair, you're going to stay exactly where you are because you've got two balanced forces enacting upon you. Whereas if forces are unbalanced, we'll have different arrow sizes, and we'll see either it changes shape or it accelerates or decelerates. I'm going to summarize all this up in a table here. If you're trying to learn anything in particular from today, memorize this table, all right? This table shows the differences between having balanced and unbalanced forces and when an object remains where it is or it's moving. Okay, so if an object stays still and has balanced forces on it, if an object remains where it is and has balanced forces enacting upon it, it'll stay still, it'll remain exactly where it is. That's like this Rubik's Cube here. But if it's moving, it can still have balanced forces applied to it. People always forget this, but say you've got a car that's moving and it's traveling at 40 miles an hour, 40 kilometers an hour, let's say, and it's staying at that constant speed of 40 kilometers an hour, it's actually got balanced forces applied to it because the applied force from the car is equal to the force of all the wind resistance and the drag and the friction that's going back onto the car, okay? It's a balanced force if it's a constant speed. So staying at a constant speed, that's balanced. However, if it's accelerating, which means it's going faster and faster and faster and faster, that's an unbalanced force. That was the case with this bottle cap here. With the film capsule, it was unbalanced, so therefore we saw it fly up, or you did in the videos anyway. If it's got an unbalanced force and it remains where it is, we're going to see it change shape. So that's the same as when you crush a can, okay? The force of the can, I don't have a can, I've got a chip packet, but the force of the can is just like the force of this chip packet. The forces it has, the tensile strength that this chip packet has to remain in its own shape. If I apply more force to this chip packet than the chip packet is applying to me, it's going to change shape and it'll crush up. I have the power. So that's just the same as crushing a can. when you crush the can, you are applying more force to it than the can is to apply force to hold its shape. And that's an unbalanced force. It changes shape. So these are the 4 different ways that balanced and unbalanced forces can apply to objects. All right. A lot of people get these two mixed up. They're traveling at constant speed and accelerating and decelerating. Make sure you understand these two. All right. Now, there'll be some work to do to further explain what balanced and unbalanced forces are. But the last thing I want you guys to remember is this term, inertia. Inertia is the tendency of an object to resist its motion. So that can be just like my Rubik's Cube sitting on the table. The table's applying inertia to stop the Rubik's Cube from falling through or anything. It's just like when you push against an elephant here. That elephant has got so much inertia. It's stopping you from being able to push it very far. Okay. So here's another term for you guys to remember. All right. Main things for you guys to remember from this lesson is what are the 3 ways you can apply force? That's push, pull, and twist. The other one is what do forces do to an object? It can make an object stay still or move at a constant speed, accelerate or decelerate, or change shape. And how do you draw forces? All right, you draw them with these arrows pointing out from the objects. All right, so there'll be work down on the sector for you to do. But yeah, thanks for listening, guys.